clamp meter functions using Hall sensor technology. The Hall effect refers to the generation of a voltage difference within a conductor when it is positioned perpendicular to a magnetic field. In the context of the amp clamp, when the clamp is placed around a conductor carrying current, a magnetic field generated by the current induces a voltage in the Hall sensor. This induced voltage exhibits a direct proportionality to the magnitude of the current flowing through the conductor. To ensure that the measurement remains unaffected by the conductor's precise location within the clamp and to enhance the overall sensitivity of the device, many Hall sensors are frequently employed and interconnected in a series configuration. Subsequently, the output signal derived from the Hall sensor or sensors is transmitted to the remaining components of the meter. Within the meter, the signal is either displayed directly or transformed into alternative formats. A prevalent example of such a transformation is the conversion of the signal into a 4 to 20 mA signal, which is particularly useful for facilitating remote measurement applications. The Hall effect is a phenomenon observed when a current-carrying conductor or semiconductor is placed in a magnetic field perpendicular to the direction of current flow. This creates a voltage difference across the conductor, perpendicular to both the current and the magnetic field. This voltage difference is known as the Hall voltage. The underlying principle involves the Lorentz force, which acts on moving charge carriers, deflecting them to one side of the conductor. The accumulation of charge carriers on one side creates an electric field that opposes further deflection. A stable state is reached when the electric force due to the Hall voltage balances the magnetic force due to the Lorentz force. The magnitude of the Hall voltage is directly proportional to the current magnetic field strength and inversely proportional to the charge carrier density and the thickness of the conductor. Hall effect sensors are widely used in various applications, including current sensing, position sensing, and magnetic field measurement. In current sensing, Hall effect sensors are used to measure the current flowing through a conductor without making direct electrical contact. This is particularly useful in applications where it is difficult or impossible to break the circuit to insert a traditional current meter. The Hall effect sensor is placed near the conductor, and the magnetic field generated by the current flowing through the conductor is measured. A Hall voltage produced by the sensor is proportional to the current flowing through the conductor. This voltage can then be amplified and displayed on a meter. In position sensing, Hall effect sensors are used to detect the position of a moving object. A magnet is attached to the moving object, and the Hall effect sensor is placed near the magnet. As the object moves, the magnetic field experienced by the sensor changes, which produces a corresponding change in the Hall voltage. This voltage can then be used to determine the position of the object. In magnetic field measurement, Hall effect sensors are used to measure the strength and direction of a magnetic field. The Hall voltage produced by the sensor is proportional to the magnetic field strength. The direction of the Hall voltage depends on the direction of the magnetic field. Clamp meters are an indispensable tool for electricians and technicians, providing a safer and convenient way to measure current without interrupting a circuit. These meters utilize the principle of electromagnetic induction, specifically the Hall effect, to determine the current flowing through a conductor. The user simply clamps the meter around the wire, and the device displays the current reading. This non-contact measurement is crucial in situations where breaking the circuit is not feasible or safe. Conventional ammeters require the circuit to be broken, so that the meter can be inserted in series with the load. This process can be time-consuming and potentially hazardous, especially in high current or high voltage applications. Clamp meters eliminate these risks by measuring the magnetic field surrounding the conductor. The magnetic field is directly proportional to the current flowing through the wire, allowing the meter to accurately determine the current value. The core component of a clamp meter is the Hall effect sensor. The Hall effect is a phenomenon where a voltage is produced across a conductor when it is subjected to a magnetic field perpendicular to the direction of current flow. In a clamp meter, the Hall effect sensor is placed within the jaws of the clamp. When the clamp is placed around a current-carrying conductor, the magnetic field generated by the current interacts with the Hall effect sensor, producing a voltage. This voltage is then processed by the meter's internal circuitry to calculate and display the current reading. The accuracy of a clamp meter depends on several factors, including the quality of the Hall effect sensor, the design of the clamp, and the calibration of the meter. High-quality clamp meters typically employ multiple Hall effect sensors to improve accuracy and reduce the effects of external magnetic fields. The clamp itself is also designed to concentrate the magnetic field around the sensor, enhancing the sensitivity of the meter. Clamp meters come in various types, each designed for specific applications. Alternating current, or AC clamp meters, are used to measure alternating current, which is the type of current used in most homes and businesses. Direct current, or DC clamp meters, are used to measure direct current, which is the type of current used in batteries and electronic devices. Some clamp meters can measure both alternating current and direct current. In addition to measuring current, some clamp meters can also measure voltage, resistance, and other electrical parameters. These meters are often referred to as multimeter clamp meters. They provide a versatile tool for electricians and technicians, allowing them to perform a wide range of electrical measurements with a single device. When using a clamp meter, it is important to follow safety precautions. Always ensure that the meter is properly calibrated and that the clamp is fully closed around the conductor. Avoid using clamp meters in wet or damp environments, and never use them on conductors that are carrying voltages above the meter's rated capacity. Clamp meters offer a safe and efficient way to measure current in various electrical applications. The non-contact measurement eliminates the need to break the circuit, reducing the risk of electrical shock and simplifying the measurement process. By understanding the principles behind clamp meters and following safety precautions, electricians and technicians can effectively utilize these tools to troubleshoot electrical problems and ensure the safe operation of electrical systems. Clamp meters are essential tools for electrical professionals due to their safety, convenience, and versatility. They allow for the non-intrusive measurement of current, which is crucial for diagnosing electrical issues without disrupting circuits. Here are some key aspects of clamp meters. Firstly, safety. Clamp meters enhance safety by allowing current measurements without breaking the circuit. This reduces the risk of electrical shock, especially in high-voltage environments. Traditional ammeters require the circuit to be opened and the meter inserted in series, which can be hazardous. Secondly, convenience. Clamp meters are easy to use. Simply clamp the jaws around the conductor to measure the current. This is particularly useful in situations where access to the wiring is limited or when the circuit cannot be easily de-energized. Thirdly, versatility. Many clamp meters can measure other electrical parameters such as voltage, resistance, capacitance, and frequency. This makes them a versatile tool for a wide range of electrical troubleshooting and maintenance tasks. Fourthly, types of clamp meters. There are two main types of clamp meters: AC clamp meters and DC clamp meters. AC clamp meters use the principle of electromagnetic induction to measure alternating current. They typically use a transformer core that is opened and clamped around the conductor. DC clamp meters use the Hall effect sensor to measure direct current. The Hall effect sensor measures the magnetic field produced by the current flowing through the conductor. Fifthly, Hall effect sensors. Hall effect sensors are semiconductor devices that produce a voltage proportional to the magnetic field passing through them. This voltage is then used to calculate the current flowing through the conductor. Hall effect sensors are more sensitive than traditional current transformers, allowing them to measure both AC and DC currents. Sixthly, measurement range and accuracy. Clamp meters are available with different measurement ranges and accuracy levels. It is important to choose a clamp meter that is appropriate for the application. For example, a clamp meter used for measuring small currents in electronic circuits will need to be more accurate than a clamp meter used for measuring large currents in industrial applications. Seventhly, jaw size. The jaw size of the clamp meter determines the maximum conductor size that can be measured. It is important to choose a clamp meter with a jaw size that is large enough to accommodate the conductors being measured. Eighthly, true root mean square or true RMS. True RMS clamp meters are used to measure the true RMS value of alternating current and voltage. This is important when measuring non-sinusoidal waveforms, such as those produced by electronic devices. Standard clamp meters only measure the average value of the waveform, which can lead to inaccurate readings. Ninthly, safety features. Clamp meters should have safety features such as overvoltage protection, overload protection, and insulated jaws. These features help to protect the user from electrical shock and prevent damage to the meter. Tenthly, applications. Clamp meters are used in a wide range of applications, including electrical troubleshooting, maintenance, and installation. They are used by electricians, technicians, and engineers in residential, commercial, and industrial settings. When selecting a clamp meter, consider the following factors. Firstly, type of current, AC or DC. Secondly, measurement range. Thirdly, accuracy. Fourthly, jaw size. Fifthly, true RMS capability. Sixthly, safety features. And seventhly, application. Clamp meters are indispensable tools for electrical professionals, offering a safe, convenient, and versatile way to measure current and other electrical parameters. By understanding the different types of clamp meters and their features, users can choose the right tool for the job and ensure accurate and reliable measurements. The Hall effect is a fascinating phenomenon with numerous practical applications, particularly in current sensing technologies like clamp meters. To fully appreciate its role, it's essential to delve into the underlying physics and the advantages it offers over traditional current measurement methods. The fundamental principle behind the Hall effect lies in the interaction between moving charges and a magnetic field. When a current-carrying conductor is placed in a magnetic field, the moving charge carriers, typically electrons, experience a force known as the Lorentz force. This force is perpendicular to both the direction of current flow and the magnetic field. As a result, the charge carriers are deflected to one side of the conductor, creating an accumulation of charge on that side. This charge imbalance generates an electric field, known as the Hall field, which opposes further deflection of the charge carriers. A stable equilibrium is reached when the electric force due to the Hall field balances the magnetic force due to the Lorentz force. The voltage difference created by the Hall field is known as the Hall voltage, and its magnitude is directly proportional to the current, the magnetic field strength, and the properties of the conductor. The Hall voltage can be expressed by the equation volts Hall is equal to capital K times capital I times capital B divided by small t, where volts Hall represents the Hall voltage, capital K is the Hall coefficient, a material property that depends on the type and concentration of charge carriers in the conductor. Capital I is the current flowing through the conductor, capital B is the magnetic field strength, and small t is the thickness of the conductor. In a clamp meter utilizing the Hall effect, a Hall effect sensor is positioned within the jaws of the clamp. When the clamp is placed around a current-carrying conductor, the magnetic field generated by the current permeates the Hall effect sensor. The sensor then produces a Hall voltage proportional to the magnetic field strength, which is directly related to the current flowing through the conductor. The meter's internal circuitry processes this Hall voltage to calculate and display the current reading. The Hall effect offers several advantages over traditional current measurement methods, such as using a shunt resistor. Firstly, non-intrusive measurement. Hall effect sensors allow for non-contact current measurement, eliminating the need to break the circuit. This is particularly useful in high current or high voltage applications where breaking the circuit can be dangerous or impractical. Secondly, isolation. The Hall effect sensor provides electrical isolation between the current-carrying conductor and the measurement circuitry. This enhances safety and prevents ground loops, which can introduce errors in the measurement. Thirdly, wide bandwidth. Hall effect sensors can measure both AC and DC currents with a wide bandwidth, making them suitable for a variety of applications. Fourthly, high sensitivity. Hall effect sensors are highly sensitive to magnetic fields, allowing for accurate measurement of small currents. Fifthly, linearity. Hall effect sensors exhibit good linearity, meaning that the output voltage is directly proportional to the current being measured. This simplifies the calibration and signal processing requirements. Sixthly, robustness. Hall effect sensors are robust and can withstand harsh environmental conditions such as high temperatures and vibrations. The accuracy of a Hall effect-based clamp meter depends on several factors, including the quality of the Hall effect sensor, the design of the clamp, and the calibration of the meter. High-quality clamp meters typically employ multiple Hall effect sensors to improve accuracy and reduce the effects of external magnetic fields. The clamp itself is also designed to concentrate the magnetic field around the sensor, enhancing the sensitivity of the meter. Furthermore, temperature compensation circuits are often incorporated to minimize the effects of temperature variations on the sensor's performance. Hall effect sensors are used in a wide range of applications beyond clamp meters. These include current sensing in power supplies, motor control systems, and automotive electronics, position sensing in rotary encoders, linear position sensors, and proximity switches. Magnetic field measurement encompasses magnetometers and scientific instruments. As technology advances, Hall effect sensors are becoming smaller, more sensitive, and more cost-effective, further expanding their applications in various fields. In summary, the Hall effect is a fundamental physical phenomenon that enables non-contact current measurement with numerous advantages over traditional methods. Hall effect-based clamp meters provide a safe, convenient, and accurate way to measure current in a variety of electrical applications. The technology continues to evolve, promising even more innovative applications in the future.